Imagine standing at the edge of the ocean at midnight. The water before you holds 300 million cubic miles of liquid, quadrillions of tons, an incomprehensible weight spread across 70% of our planet's surface. It has been here, moving, breathing, for billions of years. And right now, it is rising, not because of a storm, not because of wind. The air is perfectly still, the sky is clear, and the moon hangs above you like a pearl suspended in black velvet. The ocean is rising because the moon is pulling it. But here's what should stop you in your tracks. The moon is not touching the water. It is not pushing wind across the surface. It is simply existing 240,000 miles away in the vacuum of space. And somehow, across that impossible distance, across the void where nothing exists, it is reaching down and lifting entire oceans. How? How does emptiness carry force? How does the moon, a dead rock with no air, no warmth, no life, command the living seas of Earth? It is not magic. This is gravity. But gravity is so much stranger than we've been taught. Tonight, we're going to slow down. We're going to watch the invisible threads that bind the cosmos. We're going to see how the moon doesn't just move water. It moves time itself. How every wave that touches the shore is an echo of a conversation between worlds. How the rhythm of the tides is the heartbeat of deep time, a pulse that has shaped not just oceans but the very evolution of life. We're going to understand slowly and completely how the moon moves the tides. And by the end, you'll never look at the ocean or the moon the same way again. Let's begin. Gravity and the invisible threads. Close your eyes for a moment. Imagine you are a single molecule of water, not metaphorically. Actually, imagine it. You are two hydrogen atoms bonded to one oxygen atom tumbling through the darkness of the deep ocean. Around you, billions upon billions of your siblings press close, a liquid constellation stretching in every direction. Above you, miles of water. Below you, miles more, until finally the cold stone of the ocean floor. You have no eyes, no ears, no sense of up or down in any conventional way. But you feel something. A pull. It is so gentle that if you were alone, you might not notice it at all. But you are not alone. You are part of something vast, an ocean that covers most of this planet, a body of water so immense that its weight could crush mountains. And right now, in this moment, that entire ocean is being lifted. Not by wind, not by heat, not by any force you can see or touch. By the moon, 240,000 miles above you, hanging in the vacuum of space. A sphere of ancient stone is pulling you upward, and somehow across all that emptiness, across the void where nothing exists, no air, no water, no medium of any kind, you feel its call. How does the moon reach across 250,000 miles of absolute nothingness and move you? This is the question we're going to answer, slowly, carefully, with the kind of attention it deserves. Because the answer is not simple. The answer will take us into the deepest nature of reality itself, into the fabric of space and time, into the geometry of existence, into forces so fundamental that they hold galaxies together, and yet so subtle that you've never consciously felt them. The answer is gravity. But gravity is not what you think it is. For most of human history, gravity was a mystery wrapped in an observation. Things fall. That much was obvious. Drop a stone, and it falls. Always down. Always toward the earth. For thousands of years, this seemed like an inherent property of matter. Heavy things want to fall, the way fire wants to rise. Then Isaac Newton looked up at the moon and realized something extraordinary. The moon is falling. It is falling toward Earth right now, and it has been falling for billions of years. But it never gets closer because it is also moving sideways, fast enough that as it falls, the Earth curves away beneath it. The moon is in perpetual freefall, tracing an endless circle around our world, and the force that pulls the moon is the same force that pulls the apple from the tree, gravity. Newton gave us the mathematics. He showed us that every object with mass attracts every other object with mass, with a force proportional to their masses and inversely proportional to the square of the distance between them. This was revolutionary. This meant the cosmos was unified. The same laws that governed a falling leaf also governed the motion of planets. But Newton couldn't tell us why. Why does mass attract mass? What is the mechanism? How does the Earth know the moon is there? How does the moon know to fall? For 200 years, this remained a mystery. And then Albert Einstein looked at the problem from a different angle, and he saw something that changed everything. Gravity is not a force. Gravity is the shape of space itself. Imagine you are standing on a trampoline. The fabric beneath your feet is flat, taut, stretched evenly in all directions. Now imagine placing a bowling ball in the center. The fabric curves. It sinks down around the ball, creating a depression, a well in the surface. Now roll a marble across the trampoline. If you roll it far from the bowling ball, it travels in a straight line. But if you roll it near the depression, something interesting happens. The marble's path curves. It bends toward the bowling ball, not because the bowling ball is pulling it with some invisible tether, but because the marble is following the curved surface of the trampoline. The marble is still traveling in a straight line, but in curved space, straight lines are curved. This is Einstein's insight. Mass doesn't pull on other mass. Mass curves the fabric of space-time, and other objects move along those curves. The Earth doesn't pull the moon with an invisible rope. The Earth bends space-time around itself, and the moon follows that curvature, like a marble rolling around the depression created by a bowling ball. But here's what makes this profound. Space-time is not a metaphor. It is not a convenient visualization. Space-time is the actual structure of reality. You are not moving through space and time. You are moving within a four-dimensional fabric that can be stretched, compressed, twisted, and curved. And every object with mass curves this fabric. You curve space-time. The chair you're sitting on curves space-time. The Earth curves space-time dramatically. The sun curves it even more. And the moon, our constant companion, our ancient partner in this cosmic dance, curves space-time in a way that reaches across the void and touches the oceans of Earth. Moon is not large, as celestial objects go. It is about 1/4 the diameter of Earth. Its mass is only 1.2% of Earth's mass. If you could place the moon on a cosmic scale, it would barely register compared to the gas giants of our solar system. Jupiter has more than 26,000 times the moon's mass. But the moon is close, and in the mathematics of gravity, distance is everything. The strength of gravitational attraction falls off with the square of distance. Double the distance, and the force becomes 1/4 as strong. Triple the distance, and it becomes 1/9. This inverse square law means that proximity matters far more than you might intuitively expect. The moon is, on average, 238,855 miles from Earth. In cosmic terms, this is nothing. This is next door. This is intimate. And so, despite its small size, the moon's gravitational influence on Earth is profound. But here's what's crucial to understand. The moon doesn't just pull on Earth as a whole. It pulls on every part of Earth individually, and because Earth is not a point but an extended body, a sphere 8,000 miles in diameter, different parts of Earth are at different distances from the moon. The side of Earth facing the moon is about 4,000 miles closer to the moon than Earth's center. The side facing away is about 4,000 miles farther. And this difference, this gradient in gravitational force, is what creates the tides. Let's slow down and really see this. Imagine 3 water molecules. The first is on the surface of the ocean, on the side of Earth facing the moon. Let's call this molecule near. The second is at the center of the Earth, deep within the molten iron core. Let's call this molecule center. It's not actually water down there, but bear with the thought experiment. The third is on the surface of the ocean, on the opposite side of Earth, facing away from the moon. Let's call this molecule far. All 3 molecules feel the moon's gravity, but they don't feel it equally. Near is closest to the moon. The moon's gravitational pull on near is strongest. Center is farther away. The pull is weaker. Far is farthest. The pull is weakest of all. Now, if Earth were a rigid, undeformable point, this wouldn't matter. The whole planet would accelerate toward the moon as a unit, and everything would move together. But Earth is not a point. Earth is a body, and different parts of that body are being pulled with different strengths. Near is being pulled toward the moon harder than center is. So relative to the center of the Earth, near is being pulled away from the center, toward the moon. Far is being pulled towards the moon less than center is. So relative to the center of the Earth, far is being left behind. It's effectively being pulled away from the center in the opposite direction. Do you see it? The moon's gravity doesn't just pull Earth. It stretches Earth. It pulls the near side toward the moon and allows the far side to drift away, creating a gentle elongation along the Earth-Moon axis. This stretching force, this differential gravity, is called a tidal force. And because water is fluid, because it can flow and reshape itself in ways that solid rock cannot, the ocean responds to this stretching immediately. Water on the near side flows toward the moon, creating a bulge. Water on the far side flows away from Earth's center, creating another bulge, two bulges, one facing the moon, one facing away. This is the fundamental architecture of the tides. But we're not done yet, because there's another layer to this story, one that's often overlooked. The moon doesn't orbit around the Earth. Not exactly. What actually happens is this. The Earth and moon orbit around their common center of mass, a point called the barycenter. If two objects in space have equal mass, the barycenter is exactly halfway between them. They orbit around a point in empty space, like two dancers holding hands and spinning. But Earth and moon don't have equal mass. Earth is 88 times more massive. So the barycenter is much closer to Earth's center than to the moon's center. In fact, the barycenter is about 2,900 miles from Earth's center, which means it's actually inside Earth, about 1,000 miles beneath the surface. So the moon orbits around this point, and Earth also orbits around this point. Both bodies are in motion, both falling through space together, locked in a gravitational embrace that has lasted for more than 4 billion years. Every month, the moon completes one orbit, and every month, Earth wobbles slightly, tracing a small circle around the barycenter. This is important because it means Earth is not stationary. Earth is accelerating, constantly changing direction as it orbits the barycenter, and this acceleration affects how we perceive the tidal forces. From our perspective on Earth's surface, it feels like the moon is pulling the near-side ocean toward itself and pulling the far-side ocean also away from Earth. But from an outside perspective, what's really happening is that the moon and Earth are both falling around their common center, and the tidal bulges are the natural result of different parts of Earth being at different distances from the center of this orbital motion. It's a dance, a gravitational waltz, two partners spinning through the void, and the oceans of Earth are the flowing fabric of the dress, swirling in response to the motion. Let's return to you, standing at the edge of the ocean at midnight. The moon hangs above you, silver and silent. Beneath your feet, the Earth is solid, unmoving, it seems, eternal. But now you know the truth. The ground beneath you is rising and falling by nearly a foot every 12 hours. The solid rock is breathing with the moon's passage, flexing like a slow heartbeat made of stone. The water before you is rising even more dramatically, several feet perhaps depending on where you are. In some places on Earth, the tidal range is 50 feet. In others, it's mere inches. The local geography, the shape of the coastline, the depth of the ocean floor, the width of the bay, amplifies or dampens the effect. But everywhere on this planet, the ocean is responding to the moon. And it's not just responding to the moon's position. It's responding to the shape of space-time itself, to the curvature that the moon creates in the fabric of reality. You cannot see this curvature. You cannot touch it. But it is as real as the water, as real as the moon, as real as the ground beneath your feet. Gravity is not a force reaching across space. Gravity is space itself, bent and curved by the presence of mass. And the tides are the ocean's way of showing you this invisible architecture. Let's linger here for a moment. Let's slow down even further and really see what's happening at the molecular level. You are that water molecule again. You are tumbling in the darkness of the deep ocean, surrounded by countless others. Each molecule is bound to its neighbors by hydrogen bonds, weak electrical attractions that form and break trillions of times per second. These bonds give water its fluidity, its ability to flow and reshape itself. And right now those bonds are being gently, almost imperceptibly stretched. The molecule above you is being pulled slightly more toward the moon than you are. The molecule below you is being pulled slightly less. The difference is infinitesimal, a force so small that if you were a single molecule in isolation, you would never notice it. But you are not in isolation, you are part of an ocean. And when trillions upon trillions of molecules all experience the same infinitesimal force, the cumulative effect is staggering. The ocean rises, not quickly, not violently, but with the slow, inexorable patience of geological time. The water flows. Molecules shift position, sliding past one another, rearranging themselves into a new configuration. The surface of the ocean, that boundary between liquid and air, lifts upward inch by inch, foot by foot. And if you were standing on the shore, you would see the waterline creep higher. You would see the dry sand become wet. You would see the ocean reclaim territory it had abandoned hours before. This is high tide. And it is happening because the moon, 240,000 miles away, has curved space-time in such a way that the ocean has no choice but to respond. The moon is full tonight. Let's say that. Let's place ourselves in this moment fully. The moon is full and its light is falling on the ocean. Photons, particles of light that are also waves of electromagnetic energy, are streaming from the sun, traveling 93 million miles through space, striking the moon's surface and bouncing off. Some of those photons travel another 250,000 miles to Earth, pass through the atmosphere, and strike the surface of the ocean. And when they do, something beautiful happens. The ocean is not smooth. It is textured with waves, small ripples created by wind, larger swells created by distant storms, and the slow, deep undulations created by the tidal forces themselves. Each wave is a curve, a slope, an angle. And each angle reflects moonlight in a different direction. From your perspective on the shore, you see a path of light stretching across the water toward the moon, a shimmering road of silver that seems to lead directly to the lunar surface. This is not a single beam. It is thousands of reflections, each from a different wave, each at a slightly different angle, all combining to create the illusion of a continuous path. And that path is moving, because the waves are moving, because the water is rising, because the tide is coming in. The moonlight dances on the surface of the tidal bulge, and you are watching gravity made visible, not just in the rising water, but in the light itself, bending and reflecting off the curved surface of an ocean that is being reshaped by the curvature of space-time. Look down at your feet. The sand beneath you is wet. It is dark, saturated with seawater. A few hours ago, this sand was dry, warm from the sun, light in colour, but the tide has come in, and the ocean has touched it, and now the sand holds the memory of that touch. Each grain of sand is a tiny fragment of rock, quartz, feldspar, bits of shell, minerals worn down by eons of erosion, and each grain is surrounded by a thin film of water, held in place by surface tension and capillary action. The water fills the spaces between grains, turning the sand from a loose, dry powder into a firm, compact surface. You can walk on it without sinking. You can see your footprints pressed into it, sharp and clear. And if you look closely, really closely, you can see the boundary. There is a line in the sand, a subtle change in colour and texture, marking the highest point the water reached. Above this line, the sand is dry, loose, pale. Below it, the sand is wet, firm, dark. This line is the signature of the tide. It is the moon's handwriting inscribed in sand and water. And it is moving. As the tide continues to rise, the line creeps higher up the beach. As the tide eventually falls, the line will retreat, leaving behind a new boundary, a new mark. The sand remembers, the sand records. The sand is a witness to the invisible forces that move the ocean. Look up now. The moon is bright, yes, but it is not alone. Behind it, beyond it, the stars are scattered across the sky like dust on black velvet. Each star is a sun. Many of them have planets. Some of those planets may have moons. And on some of those moons, perhaps, there are oceans. And if there are oceans, there are tides. Because gravity is universal. It is not unique to Earth and Moon. It is a fundamental property of mass and space-time, operating the same way everywhere in the cosmos. On Titan, Saturn's largest moon, there are lakes of liquid methane, and those lakes have tides, not from a moon, but from Saturn itself, pulling and stretching Titan's surface. On Europa, one of Jupiter's moons, there is an ocean of liquid water beneath a shell of ice, and that ocean is kept liquid by tidal heating, the friction generated by Jupiter's immense tidal forces flexing Europa's interior. On distant exoplanets orbiting distant stars, there may be oceans we will never see, rising and falling in response to moons we will never name. The tides are not ours alone. They are a cosmic phenomenon, a conversation between bodies in space, written in the language of gravity. And the stars above you, those distant witnesses, are all participating in the same conversation. Every star pulls on every other star. Every galaxy pulls on every other galaxy. The entire universe is a web of gravitational relationships, a vast network of invisible threads connecting everything to everything else. You are standing on a beach, watching the tide come in. But you are also standing in the middle of the cosmos, watching the fundamental forces of nature at work. So let's return to the question we started with. How does the moon move the ocean? Not with a rope, not with a chain, not with any physical connection. The moon moves the ocean by being, by existing, by having mass. That mass curves space-time, and that curvature extends outward in all directions, weakening with distance but never disappearing entirely. The Earth sits in that curved space-time, and the Earth's oceans, fluid, responsive, free to flow, reshape themselves to match the curvature. The result is a bulge. Two bulges, actually, one toward the moon, one away from it. And as the Earth rotates beneath these bulges, we experience the rhythm of the tides, the rising and falling of the sea, twice a day, every day, for as long as the moon has existed. This is gravity, not a force, but a geometry, not a pull, but a curvature. And the tides are the proof. The tides are the visible manifestation of invisible threads that connect the moon to the Earth to the sun to the galaxy to the universe. We are all bound together, not by chains, but by the shape of space-time itself. And every wave that touches the shore is a reminder of this connection. But there's more to this story, because the bulges don't just sit there. They don't just point toward and away from the moon, static and unchanging. The Earth is spinning. The Earth is rotating beneath these bulges, carrying you, standing on the shore, through them. And this rotation, this movement through the tidal bulges, creates the rhythm of time itself. The rhythm of the tides is the rhythm of the Earth's rotation, measured in water. And that rhythm is changing. The Earth is slowing down, the moon is moving away, the dance is evolving. But to understand that, we need to see how the Earth's shape is being deformed, not just by the moon's gravity, but by the Earth's own spin, by the friction of water against stone, by the slow, patient forces that reshape planets over billions of years. We need to see the planet itself, breathing. The Earth is not solid. I know how that sounds. You're standing on ground that feels as firm as anything you've ever known. Bedrock, stone, the foundation of continents. It seems permanent, unchanging, eternal. But it's not. The Earth is elastic. It bends. It flexes. It breathes. Right now, as you read these words, the ground beneath you is rising and falling by nearly a foot, 30 to 40 centimeters, every 12 hours. The solid crust of the planet, miles of rock and metal, is being gently squeezed and stretched by the moon's gravity. You don't feel it because everything around you is moving with you. The buildings, the trees, the mountains, all of it rises and falls together, like passengers on a ship riding a slow, deep swell. But it's happening. The Earth has tides, not just the ocean, the Earth itself. And to understand why the ocean responds the way it does, why there are 2 high tides each day, why the water bulges both toward and away from the moon, we need to see the planet not as a rigid sphere, but as a soft body being reshaped by invisible hands. Let's slow down. Let's look closely at what's actually happening. Return with me to that water molecule. You are floating in the ocean, somewhere in the vast Pacific. It is midnight. The moon is directly overhead, hanging at its zenith. You feel the pull. We established this in part 1. The moon's gravity is tugging on you ever so gently, pulling you upward toward the lunar surface. But now let's add precision. Let's add numbers. You are on the surface of the ocean, on the side of Earth facing the moon. The distance from you to the moon's center is approximately 234,000 miles. That's the Earth-Moon distance, 238,055 miles, minus Earth's radius, about 4,000 miles. Now imagine another water molecule at the center of the Earth. That molecule is 238,855 miles from the moon, and a third molecule on the opposite side of Earth, facing away from the moon. That molecule is about 243,000 miles from the moon, the Earth-Moon distance plus Earth's radius. 3 molecules, 3 distances, 3 different gravitational forces. The force of gravity follows an inverse square law. Double the distance, and the force becomes 1/4 as strong. But we're not doubling the distance here, we're only changing it by a few percent. The difference is subtle, but subtle, across the scale of a planet, becomes significant. The molecule on the near side experiences about 3.3% more gravitational pull than the molecule at Earth's center. The molecule on the far side experiences about 3.2% less gravitational pull than the molecule at Earth's center. These percentages are tiny. But when you apply them to the mass of an entire ocean, 1.4 billion cubic kilometers of water, weighing about 1.4 quintillion kilograms, tiny percentages become enormous forces. The near-side ocean is pulled toward the moon more strongly than the planet's center. The far-side ocean is pulled toward the moon less strongly than the planet's center. And the result is that the Earth is being stretched along the Earth-Moon axis. Imagine the planet as a water balloon. Now imagine gently squeezing it from the sides while pulling it from the top and bottom. It elongates, it becomes egg-shaped. This is what the moon does to Earth. Let's be very clear about this, because it's the heart of the tidal phenomenon. There are 2 bulges, one on the side facing the moon, one on the side facing away. The first bulge makes intuitive sense. The moon is pulling the ocean toward itself. Of course, the water rises on the near side. But the second bulge, the one on the far side, this is where people often get confused. Why does the water bulge away from the moon? The answer is not that the moon is somehow pushing the water away. The answer is more subtle, more beautiful. It's about reference frames. Imagine you're floating in space, watching the Earth-Moon system from a distance. From your perspective, both the Earth and the moon are orbiting around their common center of mass, the barycenter. The moon is pulling on every part of Earth, but it's pulling on the center of Earth more strongly than it's pulling on the far side. So the center of Earth accelerates toward the moon faster than the far side surface does. In other words, the Earth is being pulled away from the far side ocean. The ocean isn't moving away from the moon, the Earth is moving away from the ocean. And from our perspective, standing on Earth's surface, it looks like the ocean is bulging outward. Let me say this again slowly, because it's important. The near side bulge exists because the ocean is pulled toward the moon more than Earth's center is. The far side bulge exists because Earth's center is pulled toward the moon more than the far side ocean is. Both bulges are the result of differential gravity, the gradient of force across Earth's diameter. The moon doesn't pull the ocean away on the far side. The moon pulls the Earth away from the ocean. Let's add a little more precision for those who want to see the numbers. The tidal force, the force that creates the bulges, is proportional to the mass of the moon, inversely proportional to the cube of the distance, and directly proportional to the size of Earth. Notice, inverse cube, not inverse square. This is because tidal force is not about the absolute strength of gravity. It's about the difference in gravity across a distance, and that difference falls off faster than gravity itself. This is why the moon, despite being much smaller than the sun, creates stronger tides on Earth. The sun is 27 million times more massive than the moon, but it's also 390 times farther away. When you account for the inverse cube law, the sun's tidal force on Earth is only about 46% of the moon's. The moon dominates the tides, but the sun still plays a role we'll explore in part 4. For now, let's stay with the moon and see exactly how it deforms our planet. The tidal force creates what's called an ellipsoidal deformation. The Earth becomes slightly egg-shaped with the long axis pointing toward and away from the moon. For the ocean, this deformation can be several meters high, the difference between high tide and low tide. But the solid Earth also deforms. The crust rises and falls by 30 to 40 centimeters. In some places, it's even more. This is called the solid Earth tide, and it was first measured in the late 19th century using incredibly sensitive instruments called tilt meters and gravimeters. Modern measurements, using GPS satellites and laser ranging, can detect these deformations with millimeter precision. The Earth is breathing, slowly, rhythmically, in sync with the Moon's orbit. But here's something fascinating. The solid Earth doesn't respond instantly. Rock is not perfectly elastic, it's viscous. It has internal friction. When the Moon's gravity tries to deform the Earth, the rock resists. It takes time for the strain to propagate through the crust, through the mantle, through the layers of the planet. And when the Moon moves on, when its position in the sky changes, the rock doesn't immediately snap back to its original shape. It lags behind. This lag creates heat. The friction of rock grinding against rock, of crystal lattices shifting and sliding, generates thermal energy. This is called tidal heating, and it's a major source of internal heat for some moons in our solar system. Europa, one of Jupiter's moons, has an ocean of liquid water beneath its icy crust. That ocean stays liquid, despite being far from the sun, despite the cold of deep space, because Jupiter's immense tidal forces flex Europa's interior, generating enough heat to keep the water from freezing. Io, another of Jupiter's moons, is the most volcanically active body in the solar system. Its surface is covered with erupting volcanoes, spewing sulfur and molten rock into space. This happens because Jupiter's tidal forces are so strong that they literally melt Io's interior. Earth's tidal heating is much gentler. The Moon is smaller, the forces are weaker, but the principle is the same. Every time the solid Earth flexes, a tiny amount of energy is converted to heat. Over billions of years, this has contributed to the warmth of Earth's interior. The Moon is not just moving the ocean, the Moon is heating the planet. Now let's return to the ocean. Water, unlike rock, is fluid. It has almost no viscosity compared to the solid Earth. It can flow freely, rearranging itself in response to forces almost instantaneously. When the Moon's gravity creates a tidal force, the ocean responds immediately. Well, almost immediately. In reality, water has inertia, it has mass, and it takes time for that mass to accelerate, to flow from one place to another. Also, the ocean is not a smooth, uniform layer covering the Earth. It's broken up by continents, it's constrained by coastlines. It has depth variations, deep ocean basins, shallow continental shelves, narrow straits, wide bays. All of these factors affect how the ocean responds to tidal forces. In the open ocean, far from land, the tidal bulge is actually quite small, only about 1/2 meter high. You wouldn't even notice it if you were in a boat. But when that bulge encounters a coastline, when it funnels into a bay or estuary, the water has nowhere to go but up. And this is where the tides become dramatic. In the Bay of Fundy between Nova Scotia and New Brunswick in Canada, the tidal range can exceed 16 meters, more than 50 feet. Twice a day, the water level rises and falls by the height of a 5-story building. Why? Because the shape of the bay resonates with the tidal frequency. The bay is the right size and shape that the water sloshes back and forth in sync with the tidal forces, amplifying the effect. It's like pushing a child on a swing. If you push at the right frequency, matching the swing's natural period, the amplitude grows larger and larger. The Bay of Fundy is a swing being pushed by the Moon. Let's zoom out and look at the global picture. If Earth were completely covered by a uniform ocean, no continents, no variations in depth, the tidal bulges would be smooth and symmetrical. The water would rise and fall in a simple, predictable pattern. But Earth is not uniform. The ocean basins are complex, three-dimensional shapes carved by plate tectonics, volcanic activity, and erosion over hundreds of millions of years. The Atlantic Ocean is relatively narrow and deep. The Pacific is vast and varied. The Indian Ocean is constrained by land masses on 3 sides. Each basin responds to tidal forces differently. In some places, the tides are amplified. In others, they're dampened. The Mediterranean Sea, for example, has very small tides, often less than 30 centimeters. This is because the Mediterranean is almost entirely enclosed, connected to the Atlantic by the narrow Strait of Gibraltar. The tidal bulge from the Atlantic can't easily flow into the Mediterranean, so the water level barely changes. In contrast, the English Channel, the North Sea, and the coasts of Alaska experience large tidal ranges because of their shape and depth. Oceanographers use computer models to simulate these effects. They divide the ocean into millions of small cells and calculate how water flows from one cell to another in response to tidal forces, taking into account depth, coastline shape, and the Coriolis effect, the apparent deflection of moving water due to Earth's rotation. The result is a complex, beautiful pattern of tidal currents and water level changes that varies from place to place. They are local, they are shaped by geography. Here's something to consider. The tidal bulges are always there. They don't appear and disappear. They don't turn on and off. The bulges are a permanent feature of Earth's oceans, always aligned, more or less, with the moon. What changes is your position relative to the bulges. As Earth rotates, you rotate through the bulges. You pass through the first bulge, high tide, then into the trough between bulges, low tide, then through the second bulge, high tide again, then into the second trough, low tide again. This takes about 24 hours and 50 minutes, slightly longer than a day because the moon is also moving in its orbit, and Earth has to rotate a little extra to catch up. So from your perspective, standing on the shore, the tide comes in and goes out twice a day. But from the moon's perspective, the bulges are stationary, and the Earth is spinning beneath them. It's all a matter of reference frame, and this is important because it helps us understand what happens next, what happens when we add Earth's rotation into the picture more carefully. Because the bulges don't stay perfectly aligned with the moon. They can't. The ocean has friction. It drags against the ocean floor. It takes time to flow, and this friction, this lag, has profound consequences. It's slowing down the Earth's rotation. It's pushing the moon away. It's changing the length of the day and the distance to the moon, slowly, over billions of years. Let's return to where we started. You are standing on the shore. The moon is overhead, the tide is rising, but now you understand what's really happening. The moon's gravity is creating a gradient of force across the Earth. This gradient stretches the planet along the Earth-Moon axis, creating two bulges, one toward the moon, one away from it. The solid Earth responds by deforming slightly, rising and falling by tens of centimeters. The ocean responds more dramatically, rising and falling by meters depending on local geography. And as the Earth rotates, you move through these bulges, experiencing the rhythm of high tide and low tide. But it's not just water moving. It's not just the ocean breathing. The entire planet is breathing. The crust flexes. The mantle flows. The core shifts. The Earth is not a rigid ball of rock. It is a dynamic, living system. Not alive in the biological sense, but alive in the sense that it is constantly changing, constantly responding to forces, constantly in motion. And the moon is the conductor of this motion. Every 12 hours, the Earth inhales and exhales. Every 12 hours, the ocean rises and falls. Every 12 hours, the ground beneath your feet lifts and settles. This has been happening for more than 4 billion years. It will continue for billions more. The Earth breathes with the moon. Let me paint you a picture. Imagine you could see gravitational fields the way you see light. Imagine tidal forces were visible, glowing lines of force stretching across the planet. Brighter where the force is stronger, dimmer where it's weaker. You would see two bright spots on opposite sides of Earth aligned with the moon. These are the tidal bulges. You would see the lines of force converging on these spots, pulling water and rock toward them. You would see the Earth itself glowing with strain, the crust compressed in some places, stretched in others, the whole planet subtly egg-shaped. And you would see this pattern rotating, not because the bulges are moving, but because the Earth is spinning beneath them. From space, it would look like the Earth is wearing a belt of light that stays aligned with the moon while the planet rotates inside it. This is the invisible architecture of the tides. We can't see it with our eyes, but we can measure it with instruments. We can calculate it with mathematics. We can feel it in the rising and falling of the sea, and now you can understand it. One more thing before we move on. Water has memory. Not in the mystical sense, but in a physical sense. When the tide comes in, it brings sediment, sand, silt, organic matter. It deposits this sediment on the shore, in estuaries, in tidal flats. When the tide goes out, it carries some of that sediment away, but not all of it. Over time, layers accumulate. Each layer represents a tidal cycle. Each layer is a record of the moon's position, the strength of the tide, the season, the weather. Geologists can read these layers like pages in a book. They can see patterns, daily tides, monthly spring and neap tides, seasonal variations. In ancient rocks, they can find tidal rhythmites, sedimentary layers deposited by tides hundreds of millions of years ago. And by counting the layers, by measuring their thickness, they can determine how many tides occurred per year in the distant past. This is how we know that days were shorter in the age of dinosaurs. This is how we know the moon was closer. The water remembers. The sediment remembers. The rocks remembers. The tides are not just a present phenomenon. They are a record of deep time, written in stone. We've come a long way. We started with the simple observation that the ocean rises and falls. Now we understand that this is the result of differential gravity, the moon pulling different parts of Earth with different strengths, creating a stretching force that deforms the entire planet. We understand that there are two bulges, not one, and that both are the result of the same principle, the gradient of gravitational force across Earth's diameter. We understand that the solid Earth has tides just like the ocean, and that rock itself bends and flexes in response to the moon. We understand that local geography, the shape of coastlines, the depth of ocean basins, amplifies or dampens the tidal effect, creating the enormous variation in tidal ranges around the world. And we understand that the tides are not just a surface phenomenon. They reach deep into the planet, generating heat, shaping sediments, recording history. But there's still more to explore, because the Earth is not static. The Earth is spinning, and this spin, this rotation, interacts with the tidal bulges in a way that changes everything. It changes the length of the day. It changes the distance to the moon. It changes the future of the Earth-Moon system. To see this, we need to add time to the equation. To row, Dr. Chose. We need to watch the dance unfold over not just hours or days, but over millions and billions of years. We need to see how the tides are not just moving water, they're moving time itself. For now, rest in this understanding. The Earth is soft. The Earth is being reshaped every moment of every day by the invisible hands of gravity. And you are standing on a living planet, feeling its pulse. Time is not constant. I don't mean this in the abstract, relativistic sense, though that's also true. I mean it in a concrete, measurable way. The length of a day is changing. Right now, today, a full rotation of the Earth takes 24 hours. But this has not always been true, and it will not always be true. In the age of dinosaurs, 100 million years ago, a day was about 23 hours and 30 minutes. When the first fish crawled onto land 400 million years ago, a day was about 21 hours. When life first emerged in the oceans 3.5 billion years ago, a day may have been as short as 6 hours. The Earth is slowing down. Not quickly, not noticeably in a human lifetime, but inexorably, relentlessly, the rotation of our planet is decelerating. And the cause of this deceleration is the tides. The same tides that rise and fall on the shore twice a day are also acting as a brake on Earth's rotation, stealing angular momentum from the spinning planet and transferring it to the moon. The result: our days are getting longer and the moon is moving away. This is the rhythm of deep time. This is the conversation between Earth and moon, written in the language of physics, played out over billions of years. Let's slow down and watch it unfold. Imagine the Earth from space. It is rotating counterclockwise when viewed from above the North Pole, completing one full rotation every 24 hours. The surface at the equator is moving at about 1,000 miles per hour, faster than the speed of sound. Now imagine the tidal bulges. As we established in Part 2, these bulges are created by the moon's gravity. They are regions where the ocean and the solid Earth are slightly elevated, pointing toward and away from the moon. If the Earth were not rotating, the bulges would remain stationary, always aligned with the moon. But the Earth is rotating. And here's the key: the bulges try to stay aligned with the moon, but the Earth is spinning beneath them. From your perspective on the surface, you are rotating into the first bulge. The water rises around you. High tide. 6 hours later, you've rotated out of the bulge and into the trough between bulges. Low tide. 6 hours after that, you rotate into the second bulge. High tide again. 6 hours more, and you're in the second trough. Low tide again. This is the twice daily rhythm of the tides. But notice something. The rhythm is not exactly 12 hours. It's 12 hours and 25 minutes. Why the extra 25 minutes? Because the moon is also moving. The moon orbits the Earth once every 27.3 days, relative to the stars. This means that while the Earth is rotating, the moon is also slowly moving forward in its orbit. Imagine you're standing on the beach at midnight, and the moon is directly overhead. High tide. 24 hours later, the Earth has completed one full rotation. You're back at the same position relative to the stars, but the moon has moved forward in its orbit. It's no longer directly overhead. It's slightly ahead to the east. For the moon to be directly overhead again, the Earth has to rotate a little bit more, about 13 degrees extra, which takes about 50 minutes. So the time between one high tide and the next high tide on the same side of Earth is not 24 hours, it's 24 hours and 50 minutes. This is called a lunar day or tidal day. And it means the tides don't occur at the same time every day. If high tide is at noon today, it will be at 12:50 p.m. tomorrow and 1:40 p.m. the day after that. Coastal communities have always known this. Fishermen, sailors, tidal foragers, they all learn to read the moon's phases and predict the tides. The moon is a clock. The tides are its hands. But this clock is not keeping perfect time, because the Earth is slowing down. Here's where the story becomes profound. The tidal bulges are not perfectly aligned with the moon. In an ideal frictionless world, the bulges would point directly toward and away from the moon at all times. But the real world has friction. Water has inertia. It takes time to accelerate, to flow from one place to another. The ocean doesn't respond instantly to the moon's gravity. There's a lag. Also, water drags against the ocean floor. It encounters coastlines, underwater mountains, continental shelves. All of this creates resistance, and because the Earth is rotating, this resistance causes the tidal bulges to be carried forward by the rotation. The bulges are dragged ahead of the Earth-Moon line by a few degrees. Imagine the Earth rotating counterclockwise, and the tidal bulges trying to stay aligned with the moon, but being pulled forward by the rotation. The near-side bulge ends up slightly ahead of the moon to the east. Now, the moon's gravity is pulling on this offset bulge, and because the bulge is ahead of the moon, the gravitational pull has a component that acts backward relative to Earth's rotation. It's like a brake. The moon is pulling backward on the tidal bulge, and this creates a torque that opposes Earth's rotation. The Earth is slowing down. The deceleration is tiny, incredibly tiny. Earth's rotation is slowing by about 1.7 milliseconds per century. That means every 100 years, a day becomes 1.7 milliseconds longer. You would never notice this in your lifetime. Even over many human lifetimes, the change is negligible. But over geological time, over millions and billions of years, the effect is enormous. Let's do the math. 1.7 milliseconds per century is 17 milliseconds per 1,000 years. Over 1,000,000 years, that's 17 seconds. Over 100 million years, that's about 1,700 seconds, or roughly 28 minutes. So 100 million years ago, in the Cretaceous period, when dinosaurs walked the Earth, a day was about 23 hours and 30 minutes long. There were about 370 days in a year back then, instead of 365. And we know this not just from calculations, but from evidence. Fossil corals have growth rings, like trees. They grow a layer each day and a thicker band each year. By counting the daily layers between yearly bands, paleontologists can determine how many days were in a year when the coral was alive. Ancient corals from 400 million years ago show about 400 days per year, which means days were about 22 hours long. Even older fossils suggest even shorter days. The Earth is winding down. The rotation is slowing. Time itself is stretching. But energy is conserved. Angular momentum is conserved. If the Earth is losing rotational energy, where is that energy going? To the moon. The same tidal friction that slows Earth's rotation also creates a force on the moon. Because the tidal bulge is ahead of the Earth-Moon line, the bulge's gravity pulls the moon forward in its orbit. This forward pull accelerates the moon, giving it more orbital energy. And when an orbiting object gains energy, it moves to a higher orbit. It spirals outward. The moon is moving away from Earth at a rate of about 3.8 centimeters per year. This has been measured directly using laser ranging. During the Apollo missions, astronauts placed retroreflectors on the moon's surface, mirrors that reflect laser beams back to Earth. Scientists on Earth fire lasers at these mirrors and measure the time it takes for the light to return. By measuring this time with extreme precision, they can determine the Earth-Moon distance to within a few millimeters. And year after year, the distance increases, 3.8 centimeters per year. That's about the rate your fingernails grow. It doesn't sound like much, but over millions of years, it adds up. Over 100 million years, the moon moves about 3,800 kilometers farther away. Over 1 billion years, 38,000 kilometers, the moon is leaving us. Slowly, inevitably. Let's run the clock backward. If the moon is moving away now, it must have been closer in the past. How much closer? The moon is currently about 384,400 kilometers from Earth. On average, the orbit is slightly elliptical. If it's receding at 3.8 centimeters/year, then 1 billion years ago it was about 38,000 kilometers closer, about 346,000 kilometers away. 2 billion years ago, about 308,000 kilometers. 3 billion years ago, about 270,000 kilometers. But we can't just extrapolate linearly forever, because the rate of recession depends on the strength of the tidal forces, which depends on the distance. The closer the moon, the stronger the tides, the faster the recession. Computer models that account for this suggest that when the moon first formed, about 4.5 billion years ago, it was perhaps 15,000 to 20,000 kilometers from Earth. That's less than 1/20th of its current distance. From Earth's surface, the moon would have appeared enormous in the sky, about 15 times larger in diameter than it does today, covering more than 200 times the area. And the tides would have been catastrophic. Not the gentle rise and fall we experience today, but massive waves, hundreds of meters high, sweeping across the planet twice a day. The early Earth was a violent tidal world. The ocean was in constant, chaotic motion. Coastlines were reshaped daily, sediments were churned and mixed, and the day was much shorter, perhaps only 6 hours long. The Earth was spinning fast and the moon was close, and the two were locked in a fierce gravitational dance. How did the moon get there in the first place? The leading theory is called the giant impact hypothesis. About 4.5 billion years ago, shortly after the Earth formed, a Mars-sized object, sometimes called Theia, collided with the young Earth. The impact was unimaginably violent. It vaporized rock. It melted the Earth's crust. It ejected an enormous amount of material into orbit. This material, a mix of debris from Theia and from Earth, coalesced over time, forming the moon. The moon was born from the Earth. It is made of the same stuff we are, and from the moment of its formation, it has been slowly moving away. The tides began immediately. The moon's gravity pulled on the molten, chaotic surface of the early Earth, creating tidal bulges in the magma ocean that covered the planet, and those tidal bulges began to slow the Earth's rotation, transferring angular momentum to the moon, pushing it outward. This process has been happening for 4.5 billion years, and it will continue. Let's run the clock forward. If the moon is moving away now, what will happen in the distant future? Eventually, if nothing else intervenes, the Earth and moon will become tidally locked to each other. Tidal locking is what happens when tidal friction slows an object's rotation until it matches its orbital period. The moon is already tidally locked to Earth. It rotates once per orbit, which is why we always see the same face of the moon. In the far future, Earth will also become tidally locked to the moon. This means the Earth will rotate once per lunar orbit. The moon will hang motionless in the sky over one hemisphere, and the other hemisphere will never see the moon. A day on Earth will be as long as a month, currently about 27.3 days, but by the time tidal locking occurs, it will be much longer, perhaps 47 current days. One side of Earth will experience continuous daylight for weeks, then continuous night for weeks. The tides will nearly cease, because the tidal bulges will be locked in place, no longer rotating relative to the moon. The Earth-Moon system will have reached equilibrium. But this will take an enormously long time, perhaps 50 billion years, and the Sun will not allow it. In about 5 billion years, the Sun will exhaust its hydrogen fuel and begin to expand into a red giant. It will swell to perhaps 100 times its current size, engulfing Mercury, Venus, and possibly Earth. The moon will likely be vaporized. The tidal dance will end not in equilibrium, but in fire. But let's not dwell on the end. Let's return to the present. Right now, today, the Earth is rotating, the moon is orbiting, the tides are rising and falling, and you are standing in the middle of this process. Every wave that touches the shore is part of the mechanism that slows the Earth's rotation. Every high tide is stealing a tiny fraction of a second from the day. Every low tide is pushing the moon a tiny fraction of a millimeter farther away. You are living in a moment of transition. The Earth is not the same as it was 1 billion years ago, and it will not be the same 1 billion years from now. The day is lengthening, the moon is receding, time is stretching. But the change is so slow that it feels eternal, and in a way it is. Because the tides have been here longer than you, longer than your species, longer than most of the life on Earth. The tides are ancient. The tides are patient. The tides are the heartbeat of deep time. Let's talk about how we measure this. For most of human history, time was measured by the sun. A day was the time it took for the sun to return to the same position in the sky. But in the 20th century, we developed atomic clocks, devices that measure time based on the vibrations of atoms, which are incredibly stable and precise. And when we compared atomic time to astronomical time, time based on Earth's rotation, we found a discrepancy. Earth's rotation is not constant, it's slowing down. Some days are slightly longer than others, depending on factors like earthquakes, glacial melting, and atmospheric winds. But on average, over the long term, the days are getting longer due to tidal friction. To keep our clocks in sync with Earth's rotation, we occasionally add a leap second to our timekeeping system. Since 1972, we've added 27 leap seconds. These are tiny adjustments. 1 second here, 1 second there, but they're necessary because the Earth is not a perfect clock. Tides are stealing time from the day, and we have to account for it. Let's get a little more technical for a moment. Angular momentum is a conserved quantity in physics. In a closed system, the total angular momentum cannot change. The Earth-Moon system is not perfectly closed. There are external influences from the Sun and other planets, but to a good approximation, the total angular momentum of Earth and Moon is constant. Right now, most of that angular momentum is in Earth's rotation. The Earth is spinning fast, and it has a lot of rotational angular momentum. The Moon's orbital angular momentum is smaller, but it's increasing. As tidal friction slows Earth's rotation, rotational angular momentum is transferred to the Moon's orbit, increasing its orbital angular momentum. The total remains, approximately, constant, but the distribution changes. In the distant past, the Earth was spinning very fast and the Moon was close. In the present, the Earth is spinning slower and the Moon is farther. In the far future, the Earth will be spinning even slower and the Moon will be even farther. This is the dance of angular momentum, a slow, stately transfer of energy and motion from the Earth to the Moon, mediated by the tides. Let's visualize this more clearly. Imagine looking down at the Earth from above the North Pole. The Earth is rotating counterclockwise. The Moon is to the right. If there were no friction, the tidal bulges would point directly toward and away from the Moon. One bulge on the right side of Earth, one on the left. But because of friction, the bulges are dragged forward by Earth's rotation. The near side bulge is ahead of the Moon, slightly to the upper right. Now the Moon's gravity pulls on this bulge. The gravitational force has two components. One, a component pointing toward the Moon. This is the force that keeps the bulge aligned, more or less. Two, a component pointing backward, opposite to Earth's rotation. This is the torque that slows the rotation. Similarly, the Moon feels a gravitational pull from the offset bulge. Because the bulge is ahead of the Moon, this pull has a component that accelerates the Moon forward in its orbit. The result, Earth slows down, Moon speeds up, and moves to a higher orbit. This is the mechanism. This is how the tides act as a brake on Earth and a boost for the Moon. It's elegant, it's inevitable, it's happening right now. We can see evidence of Earth's changing rotation in unexpected places. Ice cores drilled from Antarctica and Greenland contain layers of ice, one for each year, going back hundreds of thousands of years. Within each yearly layer, there are finer layers corresponding to daily and seasonal cycles. By analyzing these layers, scientists can reconstruct not just past climates, but also subtle variations in Earth's rotation. They can see how the length of the day has changed over millennia, influenced by the melting and freezing of ice sheets, which redistributes mass and affects rotation like a spinning figure skater pulling in or extending their arms. They can see the fingerprints of tidal friction written in ice. The Earth remembers. The ice remembers. The tides leave their mark on everything. Let's bring this back to human scale. You will never notice the Earth slowing down. The change is far too small. In your entire lifetime, the day will lengthen by perhaps a few milliseconds. You will never feel it. The moon will move away by perhaps a meter or two. You will never see the difference. But you are part of the process. Every time you stand at the shore and watch the tide come in, you are watching the mechanism that is changing the Earth and the moon. Every wave is a tiny transfer of energy. Every high tide is a tiny theft of rotational momentum. You are standing in the flow of deep time, watching the universe evolve. And there's something profound about that. Because it means you are not separate from the cosmos. You are not an observer standing outside the system. You are in the system. You are part of the dance. The tides move through you. The moon's gravity pulls on the water in your body, though the effect is negligible. The Earth's rotation carries you through space at 1,000 miles per hour. You are a participant in the cosmic ballet. There's a poem by T.S. Eliot that begins, "Time present and time past are both perhaps present in time future." The tides are a manifestation of this. The present tide, the water rising at your feet right now, contains the past, the ancient moon, the young Earth, the catastrophic tides of the early solar system, and the future, the distant moon, the slow Earth, the eventual tidal locking. Every wave is a moment in a story that spans billions of years. And you are reading that story. You are standing in the middle of the sentence, watching the words unfold. The moon is the author. The tides are the text. The Earth is the page. And time is the rhythm, the meter, the beat that carries the story forward. We've seen how Earth's rotation creates the twice-daily rhythm of the tides. We've seen how tidal friction is slowing the Earth and pushing the moon away. We've seen how this process has been unfolding for billions of years and will continue for billions more. But the moon is not the only player in this story. There's another gravitational influence, one we've mentioned but not yet fully explored. The sun. The sun is much farther away than the moon, but it's also vastly more massive. And its gravity also creates tides on Earth. These solar tides interact with the lunar tides in complex and beautiful ways, creating patterns that repeat on monthly and yearly cycles. Sometimes the sun and moon work together, creating exceptionally high tides. Sometimes they work against each other, creating exceptionally low tides. This is the dance of spring and neap tides. This is the monthly rhythm that overlays the daily rhythm. And to understand it, we need to look up at the sky and see not just the moon, but the sun as well. We need to see how two celestial bodies, working in concert and in opposition, write a more complex story in the ocean. For now, rest in this understanding. The tides are not just moving water. They are moving time. They are the clock of the cosmos ticking in the rhythm of waves, measuring the slow evolution of the Earth-Moon system. And you are living in one tick of that clock, one moment in deep time, one wave in an infinite ocean. The moon is not alone in the sky. We've been focusing on the moon because it dominates the tides. Its proximity to Earth makes its gravitational influence profound, immediate, intimate. But there is another presence. Larger, more distant, more powerful in absolute terms, but gentler in its tidal effect. The sun. The sun is 27 million times more massive than the moon. Its gravitational pull on Earth is about 177 times stronger than the moon's. But the sun is also 390 times farther away, and as we learned in part 1, tidal forces depend not on the absolute strength of gravity, but on the gradient of gravity, the difference in gravitational pull across Earth's diameter. This gradient falls off with the cube of distance, so even though the sun is vastly more massive, its tidal effect on Earth is only about 46% of the moon's. The sun creates its own tidal bulges, smaller than the moon's, but still significant. And these two sets of bulges, lunar and solar, overlap, interfere, combine. Sometimes they work together, creating tides of exceptional height. Sometimes they work against each other, creating tides of exceptional modesty. This is the monthly rhythm. This is the dance of spring and neap tides. And to understand it, we need to see the sun and moon not as separate actors, but as partners in a cosmic duet. Let's start with the sun alone. Imagine for a moment that the moon doesn't exist. Earth orbits the sun, and the sun's gravity creates tidal forces on Earth. Just like the moon, the sun pulls more strongly on the near side of Earth than on the far side. This creates two tidal bulges, one facing the sun, one facing away. These bulges are smaller than the lunar bulges. If the moon's tidal effect creates a bulge of, say, 1 meter in the open ocean, the sun's tidal effect creates a bulge of about 0.46 meters, but the principle is the same. As Earth rotates, you pass through these solar bulges twice a day. High tide when you're facing the sun, low tide 6 hours later. High tide again when you're facing away from the sun, low tide again 6 hours after that. The rhythm is the same as the lunar tides, but the amplitude is smaller. Now, bring the moon back into the picture. The moon is also creating two bulges, larger than the sun's, and these two sets of bulges, lunar and solar, are both present at the same time, both trying to shape the ocean. What happens when they overlap? Once a month, the sun, moon, and Earth align. This happens twice per lunar cycle. 1 * new moon. The moon is between the Earth and the sun. From Earth, we can't see the moon because its illuminated side is facing away from us. 2 * full moon. The Earth is between the moon and the sun. From Earth, we see the entire illuminated face of the moon. In both cases, the sun, moon, and Earth are in a straight line. And when they're in a straight line, the tidal bulges align. The moon's bulge and the sun's bulge point in the same direction. They add together. The result is a tidal bulge that's larger than either would create alone, about 1.46 meters in the open ocean. 1 meter from the moon plus 0.46 meters from the sun. This creates what are called * spring tides. The name has nothing to do with the season. It comes from the Old English word springen, meaning to leap or to burst forth. During spring tides, the high tides are exceptionally high and the low tides are exceptionally low. The tidal range, the difference between high and low tide, is at its maximum. If you live near the coast, you notice this. The water comes farther up the beach than usual, it recedes farther down. The intertidal zone, the area between high and low tide, is wider, more dramatic. Twice a month, the cosmos conspires to move the ocean with maximum force. 2 weeks after the new moon, the moon has moved a quarter of the way around its orbit. From Earth, we see half of the moon's illuminated face. This is called the * first quarter moon. 2 weeks after that, the moon has moved 3/4 of the way around its orbit. We see the other half of the illuminated face. This is the * third quarter moon. In both cases, the sun and moon are at right angles to each other as seen from Earth. The sun is pulling one way, the moon is pulling another way, 90 degrees different. Now the tidal bulges don't align. They interfere. The moon is still creating its bulges, pointing toward and away from the moon. The sun is still creating its bulges, pointing toward and away from the sun, but these directions are perpendicular. The result is that the sun's bulge partially fills in the moon's trough, and vice versa. The combined tidal bulge is smaller than the moon's alone, about 0.54 meters in the open ocean. 1 meter from the moon minus 6.46 meters from the sun, though the geometry is more complex than simple subtraction. This creates what are called * neap tides. The word neap comes from Old English nep, meaning barely touching or scanty. During neap tides, the high tides are less high and the low tides are less low. The tidal range is at its minimum. The ocean's breadth becomes shallow. The intertidal zone shrinks. The water barely seems to move. Twice a month, the sun and moon work against each other, dampening the tides. Let's trace the full cycle. Day 1. New moon abstus, sun, moon, and Earth are aligned. Spring tides, maximum tidal range. The moon is invisible in the sky, or visible only as a thin crescent just after sunset. * Day 7, first quarter moon. Neap tides, minimum tidal range. The moon is half illuminated, visible in the afternoon and evening. Asterisk day 15. Full moon asterisk, sun, moon and earth are aligned again, but with earth in the middle. Spring tides, maximum tidal range. The moon is fully illuminated, rising at sunset, visible all night. Asterisk day 22, third quarter moon. The moon is 90 degrees from the sun on the opposite side. Neap tides, minimum tidal range. The moon is half illuminated, visible in the late night and morning. Asterisk day 29.5. New moon again. The cycle repeats. This is the monthly rhythm of the tides. Spring neap, spring. High low, 31st. The ocean breathes, not just with the daily rhythm of Earth's rotation, but with the monthly rhythm of the moon's orbit. And if you live by the sea, you learn to read this rhythm. You learn to watch the moon's phases and know what the tides will do. The moon becomes a calendar, written in light and water. Let's visualize this more carefully. Imagine you're looking down at Earth from above the North Pole. During a new moon, the moon is to the right, between Earth and the sun, which is farther to the right. The lunar tidal bulge points right toward the moon and sun, and left away from them. The solar tidal bulge also points right and left. They align. They add. The combined bulge is large. During a first quarter moon, the moon is above Earth in this view. The lunar tidal bulge points up toward the moon and down away from the moon. The sun is still to the right. The solar tidal bulge points right toward the sun and left away from the sun. The bulges are perpendicular. They interfere. The combined effect is smaller during a full moon. The moon is to the left, on the opposite side of Earth from the sun. The lunar tidal bulge points left toward the moon and right away from the moon. The solar tidal bulge points right toward the sun and left away from the sun. They align again. They add. The combined bulge is large. During a third quarter moon, the moon is below Earth. In this view, the lunar tidal bulge points down and up. The solar tidal bulge still points right and left. They're perpendicular again. They interfere. The combined effect is smaller. This is the geometry of spring and neap tides. It's a dance of alignment and opposition, played out in the sky and reflected in the ocean. Not all spring tides are equal. The moon's orbit around Earth is not a perfect circle. It's an ellipse. At its closest point, called asterisk 63,000 kilometers from Earth, at its farthest point, called asterisk apogee, it's about 405,000 kilometers away. That's a difference of about 42,000 kilometers, more than 10%. And because tidal forces depend on distance, inverse cube law, this makes a significant difference. When the moon is at perigee, its tidal effect is about 40% stronger than when it's at apogee. So if a spring tide coincides with perigee, the tides are exceptionally large. These are sometimes called asterisk perigee spring tides, or, colloquially, asterisk king tides. Similarly, Earth's orbit around the Sun is also an ellipse. Earth is closest to the Sun, perihelion, in early January and farthest aphelion in early July. The difference is about 5 million kilometers, about 3%. This affects the solar tides, though the effect is smaller than the Moon's orbital variation. When perihelion coincides with a spring tide, the solar contribution is maximized, and if perihelion, perigee, and a spring tide, new or full moon, all coincide, which happens rarely, the tides are at their absolute maximum. These are the highest tides of the year, sometimes of the decade. Coastal communities watch for these events. They can cause flooding, especially if combined with storms or high winds. The tides are not just predictable, they're variable, with layers of complexity built on top of the basic daily and monthly rhythms. Humans have been watching the tides for as long as we've lived near the ocean. Ancient civilizations noticed the correlation between the moon's phases and the tides. The Babylonians, the Greeks, the Polynesians, all of them tracked the moon and used it to predict the tides. But they didn't understand why. Aristotle speculated that the moon somehow breathed on the ocean, causing it to rise and fall. Pliny the Elder, a Roman naturalist, noted the connection between the moon and tides, but offered no mechanism. It wasn't until Newton that we understood the gravitational cause And it wasn't until the 19th century that we developed mathematical models sophisticated enough to predict tides accurately for any location on Earth. Today, tide tables are generated by computer models that account for the positions of the moon and sun, the shape of coastlines, the depth of the ocean, and countless other factors. But the fundamental pattern, spring and neap, high and low, the monthly and daily rhythms, has been the same for billions of years. The ancient observers were watching the same dance we watch today, the moon and sun, moving through the sky, writing their story in the water. In some rivers, the incoming tide creates a phenomenon called a asterisk tidal bore, a wave that travels upstream, against the current. This happens when the tidal range is large, often during spring tides, and the river is shallow and funnel-shaped. The rising tide enters the river mouth faster than the river can accommodate it, creating a wavefront that propagates upstream. Some tidal bores are small, just a ripple. Others are massive. The Qiantang River in China has one of the largest tidal bores in the world. During spring tides, the bore can be up to 9 meters high and travel at 40 kilometers per hour. People gather to watch it. Surfers ride it. It's a spectacle, a visible manifestation of the moon and sun's combined gravitational pull, channeled through the geometry of the river. The bore is a reminder that tides are not just about water levels rising and falling, they're about water moving, flowing, surging, reshaping the landscape. The tides are dynamic, they are alive. Let's step back and appreciate the full complexity. The tides are not a simple sine wave. They're a superposition of multiple cycles. 1. The semi-diurnal cycle, 2 high tides and 2 low tides per day, caused by Earth's rotation through the tidal bulges. Period, 12 hours 25 minutes. 2. The diurnal inequality. The 2 high tides each day are often not the same height, because the moon's orbit is tilted relative to Earth's equator. Period, 24 hours 50 minutes. 3. The fortnightly cycle, spring and neap tides caused by the alignment and opposition of the sun and moon. Period, 14.77 days. 4. The monthly cycle, variations due to the moon's elliptical orbit, perigee and apogee. Period, 27.55 days. 5. The semi-annual cycle, variations due to Earth's elliptical orbit around the sun, perihelion and aphelion. Period, 6 months. 6. The 18.6-year cycle, variations due to the precession of the moon's orbital plane. Period, 18.6 years. And there are others, smaller, more subtle cycles caused by the gravitational influences of other planets, by the shape of ocean basins, by weather patterns. When you add all of these together, you get the actual, observed tides at any given location. It's a symphony, a harmonic composition with multiple voices, multiple rhythms, all interwoven. And the ocean plays this symphony perfectly, every day, every month, every year. For centuries, predicting tides was an art as much as a science. Sailors and fishermen learned the patterns through experience. They kept records, noticed correlations, passed down knowledge through generations. In the 19th century, mathematicians began to formalize this knowledge. Lord Kelvin, a British physicist, developed a mechanical device called a asterisk tide predicting machine, a complex arrangement of gears and pulleys that could simulate the harmonic components of the tides and predict future tides for a given location. The machine was beautiful, a brass and steel embodiment of celestial mechanics, translating the motions of the moon and sun into the rise and fall of the ocean. Today, we use computers. We input the positions of the moon and sun, calculated from orbital mechanics, the shape of the coastline, the depth of the ocean, and other factors. The computer solves the equations and outputs a tide table. But the principle is the same as Kelvin's machine. The tides are predictable because they are the result of regular, repeating astronomical cycles. The moon orbits the Earth orbits the sun. These orbits are stable, governed by gravity, and they create patterns in the tides that repeat with clockwork precision. You can predict the tides years in advance, down to the minute. The ocean is a clock. The moon and sun are its hands. But nature is never perfectly simple. There are places where the tides don't follow the expected pattern. In the asterisk Gulf of Mexico, for example, the tides are mostly diurnal. one high tide and one low tide per day instead of two. This happens because of the shape and size of the Gulf. It has a natural resonant frequency that matches the diurnal component of the tidal forces more than the semi-diurnal component. In the Mediterranean Sea, as we mentioned in Part 2, the tides are very small, often less than 30 centimeters, because the sea is almost entirely enclosed. In amphidromic points, specific locations in the open ocean, there is essentially no tide at all. These are points around which the tidal wave rotates due to the Coriolis effect. At the center of the rotation, the water level doesn't change. And then there are storm surges. These can add meters to the tide, especially during hurricanes. A storm surge during a spring tide can be catastrophic. The tides are predictable, but they are not the only factor affecting sea level. Weather, climate, ocean currents, seismic activity, all of these can interfere with the tidal pattern. The ocean is complex. It is influenced by countless forces, and the tides are just one voice in a larger conversation. You're standing at the edge of the ocean. It's a full moon tonight. The moon is rising in the east, huge and orange, just above the horizon. You know now that this is a spring tide. The sun and moon are aligned. Their tidal forces are working together. The water is higher than it was last week. It's creeping farther up the beach, reaching the dry sand, the driftwood, the line of seaweed left by previous tides. In 6 hours it will recede, farther than usual, exposing rocks and tide pools that are usually submerged. And in 2 weeks, during the third quarter moon, the tides will be gentler. The water will barely move. Neap tides. You can see the pattern now. You can read the sky and know what the ocean will do. This is ancient knowledge. This is the wisdom of sailors and fishermen, of coastal peoples who have lived by the rhythm of the tides for thousands of years. But it's also modern knowledge. It's physics and mathematics, orbital mechanics and fluid dynamics. The two are not separate. They are the same understanding, expressed in different languages. The tides connect us to the cosmos. They connect us to the moon and sun, to the forces that govern the motion of planets and stars. Every wave is a reminder that we are part of something larger. Let's zoom out one more time. The Earth, the moon, the sun, 3 bodies bound by gravity moving through space together. The Earth orbits the sun. The moon orbits the Earth, and all 3 are constantly changing position relative to each other. This is called the asterisk's 3-body problem in physics, and it's notoriously difficult to solve. For 2 bodies, like the Earth and Moon alone, the mathematics is elegant. The orbits are perfect ellipses and everything is predictable. But add a 3rd body, the Sun, and the system becomes chaotic. The orbits are no longer perfect ellipses. They wobble and precess. The Moon's orbit tilts and rotates. The Earth's orbit shifts. Over long timescales, these perturbations can be significant, but over human timescales, the system is stable enough to predict. And the tides are the visible manifestation of this tree-body dance. The moon pulls. The sun pulls. The Earth responds. And the ocean rises and falls twice a day in a rhythm that has been playing for billions of years. There's something deeply poetic about spring and neap tides. Spring tides are the moments of alignment, when the cosmos speaks with one voice. The sun and moon, despite their vast differences in size and distance, work together. They harmonize. The ocean responds with maximum force. Neap tides are the moments of opposition, when the cosmos speaks with 2 voices. The sun and moon pull in different directions. They counteract each other. The ocean's response is muted, gentle. It's a metaphor for life itself. Sometimes the forces in our lives align. Everything works together. We feel powerful, capable, in sync with the universe. Sometimes the forces oppose each other. We feel pulled in different directions. Our energy is dampened. We move through the world more quietly. The tides remind us that both states are natural. Both are part of the rhythm. Alignment and opposition. Harmony and conflict. Spring and neap. The ocean accepts both. It rises and falls without judgment, without resistance. And perhaps we can learn from that. We've seen how the moon dominates the tides and how the sun modulates them. We've seen the daily rhythm, the monthly rhythm, the layers of complexity. But there's one more layer to explore. The deepest layer. The connection between the tides and life itself. Because the tides are not just a physical phenomenon, they are a biological phenomenon. The tides created the intertidal zone, the space between high and low water, the place where ocean meets land. And this zone became a crucible for evolution. This is where life first ventured out of the sea. This is where organisms learned to survive in two worlds, water and air. This is where the rhythm of the tides became written into the biology of countless species. And this is where we ultimately came from. To understand the full story of the tides, we need to see them not just as physics, but as the pulse of life. We need to see how the moon didn't just move the ocean, it moved the evolution of life on Earth. For now, rest in this understanding. The tides are not the work of one celestial body, but two. The moon and sun dancing through the sky, sometimes in step, sometimes out of step, but always moving the ocean, always writing their story in water, always reminding us that we are part of a larger system, a cosmic choreography that has been unfolding for billions of years and will continue for billions more. We've travelled far together. We've seen how gravity curves space-time, how the moon stretches the Earth, how the planet spins beneath tidal bulges, how the sun and moon dance in the sky, creating rhythms within rhythms. We've seen the physics, the mathematics, the celestial mechanics. But there's one more layer to this story, the deepest layer. The layer where physics becomes biology, where the tides stop being just about water and rock and become about life. Because for 4 billion years, life on Earth has been listening to the tides, the rhythm of the ocean, rising and falling twice a day, every day, has shaped evolution in ways both obvious and subtle. The tides created environments, they created challenges, they created opportunities. And life responded, life adapted, life evolved, life learned to dance with the moon. Let's slow down one final time and see how the tides didn't just move water, they moved the very trajectory of life on Earth. There is a place on Earth that is neither fully ocean nor fully land. It is the space between high tide and low tide, the intertidal zone. Twice a day this zone is submerged beneath seawater. Twice a day it is exposed to air. It is a harsh environment, a place of extremes. When the tide is in, organisms must cope with waves, currents, predators from the sea. When the tide is out, they must cope with desiccation, temperature fluctuations, predators from the land, the burning sun. To survive here, you must be able to live in two worlds. You must be amphibious in the broadest sense, capable of functioning both underwater and in air. And this requirement, this challenge, made the intertidal zone one of the most important evolutionary environments in Earth's history, because this is where life first left the ocean. About 400 million years ago, during the Devonian period, the first vertebrates began to venture onto land. They were fish, lobe-finned fish with muscular fins that could support their weight, and primitive lungs that could extract oxygen from air. But they didn't just suddenly decide to walk onto land one day. They were prepared by the intertidal zone. These fish lived in shallow coastal waters and tidal pools. When the tide went out, they were sometimes stranded. Those that could survive a few hours out of water, by breathing air, by keeping their gills moist, by wriggling across wet sand to reach another pool, had an advantage. They could access food that other fish couldn't reach. They could escape aquatic predators. They could exploit a new ecological niche. Over millions of years, natural selection favoured those individuals that were better at surviving on land. Fins became stronger, more limb-like. Lungs became more efficient. Skin became more resistant to drying out. Eventually, these fish became amphibians, and amphibians became reptiles, and reptiles became mammals and birds. And here we are, you and I, sitting here, breathing air, living on land, are the descendants of fish that learned to survive in tidal pools. The tides trained our ancestors to leave the ocean. But it's not just vertebrates. The intertidal zone has shaped countless lineages. Barnacles live glued to rocks in the intertidal zone. When the tide is in, they open their shells and extend feathery appendages to filter food from the water. When the tide is out, they close their shells tight, trapping moisture inside, and wait. Mussels do the same, clamping their shells shut to prevent desiccation. Sea anemones retract their tentacles and become gelatinous blobs, minimizing surface area to reduce water loss. Crabs scuttle into crevices or burrow into wet sand. Seaweed has evolved flexible, rubbery tissues that can withstand being battered by waves and then exposed to air without drying out. Each of these organisms has evolved specific adaptations to cope with the tidal rhythm. And the rhythm is predictable. It repeats every 12 hours and 25 minutes every day for millions of years. This predictability allowed life to evolve internal clocks, biological timers synchronized with the tides. Many organisms have circadial rhythms, internal biological clocks with a period of about 12.4 hours matching the tidal cycle. Fiddler crabs, for example, emerge from their burrows to feed during low tide. Even if you take them into a laboratory, far from the ocean, and keep them in constant conditions with no tidal cues, they will still follow a roughly 2.4-hour activity cycle. The rhythm is built into their biology. It's genetic. It's inherited. Oysters open and close their shells in sync with the tides. Researchers have taken oysters from the Atlantic coast and moved them to landlocked laboratories in the Midwest. For the first few days, the oysters continued to open and close according to the Atlantic tides, but gradually they shifted their rhythm to match what the tides would be if the ocean were in the Midwest, based on the moon's position in the sky. The oysters are tracking the moon even when there's no water. Marine worms, snails, fish, algae, many species show circadial rhythms, and it's not just the 2.4-hour cycle. Some organisms track the fortnightly cycle of spring and neap tides. Grunion, small fish that live along the California coast, spawn during spring tides. They ride the highest waves onto the beach, lay their eggs in the sand above the high tide line, and return to the sea. The eggs develop in the moist sand and hatch during the next spring tide 2 weeks later, when the water reaches them again. The timing is exquisite. The fish are reading the moon's phases, predicting the tides, and synchronizing their reproduction with the rhythm of the ocean. Life has internalized the tides. The moon's gravity is written into DNA. Even humans may carry echoes of tidal rhythms. The average human menstrual cycle is about 25 days, the same as the lunar month. Is this a coincidence? Maybe. The lunar month is also close to the length of many other biological cycles, and there's no clear evolutionary reason why human reproduction would be tied to the moon. But it's intriguing. Some researchers have suggested that early humans living near coasts may have been influenced by lunar cycles, perhaps through the availability of tidal food sources or through the light of the full moon affecting sleep and hormones. But the correlation is there, and even if it's just coincidence, it's a reminder that we are not separate from the cosmos. We are part of the same system that creates the tides. We are made of the same matter. We are governed by the same forces. The moon pulls on the water in our bodies, just as it pulls on the ocean. The effect is negligible, far too small to feel, but it's real. We are tidal creatures, whether we know it or not. Let's go even deeper, back to the origin of life itself. About 3.8 billion years ago, life emerged on Earth. We don't know exactly how or where, but one leading hypothesis involves tidal pools. Tidal pools are shallow depressions in rock that fill with seawater during high tide and are exposed during low tide. When exposed, the water evaporates, concentrating the dissolved chemicals, salts, minerals, organic molecules. This concentration effect could have been crucial for the origin of life. For complex molecules like RNA or proteins to form, you need high concentrations of the building blocks. In the open ocean, these molecules are too dilute, but in a tidal pool, evaporation concentrates them. Then, when the tide comes back in, the pool is replenished with fresh seawater, bringing new materials. The cycle repeats. Concentration, dilution, concentration, dilution. This creates a dynamic chemical environment, one that could drive the formation of increasingly complex molecules. Some researchers have suggested that the tides provided the energy and the rhythm necessary for life to emerge. The moon, in this view, is not just a passive observer. The moon is a midwife, actively shaping the conditions that allowed life to begin. We've talked about how the moon was much closer to Earth in the distant past. Let's revisit that, but now with an eye toward life. 4.5 billion years ago, when the moon first formed, it was perhaps 15,000 to 20,000 kilometers from Earth, less than 1/20th of its current distance. The tides were enormous, Not the gentle rise and fall we see today, but catastrophic waves hundreds of meters high, sweeping across the planet. The Earth was a violent place. The surface was molten or semi-molten. The atmosphere was toxic. The ocean was hot, acidic, churning. And yet, within a few 100 million years, life emerged. How did life survive in such a violent environment? One possibility is that the extreme tides actually helped. The tides mixed the ocean, bringing nutrients from the deep to the surface. They created tidal pools and intertidal zones, even in that harsh world. They provided energy, kinetic energy, from the moving water, thermal energy from tidal heating. The tides were destructive, yes, but they were also creative. They shaped the environment in ways that may have been essential for life to begin. As the moon moved away and the Earth's rotation slowed, the tides became gentler. The catastrophic tidal waves of the early Earth gave way to the more moderate tides we see today. And this change may have influenced the evolution of life. In the early Earth, with extreme tides, only the hardiest organisms could survive near the coast. The intertidal zone was a place of constant destruction and renewal, but as the tides moderated, the intertidal zone became more stable. It became a place where complex ecosystems could develop. Coral reefs, kelp forests, mangrove swamps, salt marshes, these are all intertidal or near-shore ecosystems that depend on relatively stable tidal conditions. If the tides were still as extreme as they were 4 billion years ago, these ecosystems couldn't exist. So the slowing of the tides, caused by tidal friction, by the moon's recession, may have been necessary for the evolution of complex life. The moon's retreat is not just a physical process. It's a biological process. It's part of the story of how life became what it is today. About 540 million years ago, something extraordinary happened. In a relatively short period of geological time, perhaps 20 to 30 million years, the diversity of life on Earth exploded. This is called the Cambrian explosion. Before the Cambrian, life was mostly simple: single-celled organisms, algae, simple multicellular creatures. After the Cambrian, the oceans were filled with complex animals. Arthropods, mollusks, echinoderms, chordates, animals with eyes, with shells, with skeletons, with predatory behaviors. What caused this explosion of diversity? There are many theories. Rising oxygen levels, genetic innovations, ecological feedback loops. But one factor that's often overlooked is the tides. By the Cambrian, the moon was farther from Earth than it had been in the early days, but still closer than it is now. The tides were stronger than today, but not catastrophically so. This created extensive intertidal zones, vast areas of shallow water that were alternately submerged and exposed. These zones were ecologically rich. They provided diverse habitats, abundant food, and strong selective pressures, organisms that could move, that could sense their environment, that could adapt to changing conditions. These organisms thrived. The tides may have been one of the driving forces behind the Cambrian explosion. The moon, once again shaping the trajectory of life. Fast forward to the present. The tides are still shaping ecosystems. Salt marshes are coastal wetlands that are flooded by tides. They are among the most productive ecosystems on Earth, providing habitat for fish, birds, and invertebrates, and acting as nurseries for many marine species. Mangrove forests grow in the intertidal zone in tropical regions. Their roots are submerged during high tide and exposed during low tide. They protect coastlines from erosion and storm surges, and they provide habitat for countless species. Coral reefs are influenced by tides. Some corals spawn in sync with the lunar cycle, releasing eggs and sperm during specific tides to maximize the chances of fertilization. Kelp forests in temperate waters are shaped by tidal currents, which bring nutrients and oxygen. All of these ecosystems depend on the tides. Remove the tides, and these ecosystems would collapse. The tides are not just a physical phenomenon, they are an ecological force. They structure communities, they drive nutrient cycles. They create the rhythm to which countless species have adapted. Humans too have always lived in relationship with the tides. Coastal peoples around the world have depended on tidal rhythms for fishing, foraging, navigation. In many cultures, the tides are woven into mythology and spirituality. The Maori of New Zealand see the tides as the breathing of the ocean, a manifestation of the god Tangaroa. The Haida of the Pacific Northwest have stories of the moon controlling the tides, rewarding or punishing humans based on their behavior. In Celtic mythology, the tides are connected to the cycles of life and death, the ebb and flow of existence. These are not just stories. They are expressions of a deep understanding, an intuitive recognition that the tides are part of something larger, something cosmic. Modern science has given us the details. We know about gravity, about differential forces, about orbital mechanics. But the ancient wisdom remains true. The tides connect us to the moon, to the sun, to the rhythms of the universe. Let's look ahead one more time. We've talked about how the moon is moving away, how the Earth is slowing down. In the far future, billions of years from now, the tides will be very different. If the Earth and Moon become tidally locked, which would take about 50 billion years longer than the Sun will last, the tides will nearly cease. The Moon will hang motionless in the sky over one hemisphere. The tidal bulges will be locked in place. There will be no daily rise and fall of the ocean. What would this mean for life? The intertidal zone would disappear. The ecosystems that depend on tidal rhythms would collapse. Species with circadtidal clocks would lose their synchronization. The evolutionary pressures that shaped so much of life would vanish. It would be a fundamentally different world. But this will not happen. The sun will not allow it. In about 5 billion years, the sun will expand into a red giant, likely engulfing the Earth and Moon. The tides will end not in stillness, but in fire. But even if the Earth survives, even if the oceans somehow persist, the tides will eventually fade. The dance will end. The rhythm that has played for 4.5 billion years will fall silent. Let's step back and see the full picture. The tides are the result of gravity, the curvature of space-time created by the moon and sun. But they are also the result of time, the slow evolution of the Earth-Moon system over billions of years. And they are also the result of life, because life has shaped the Earth, and the Earth has shaped the tides. The three are inseparable. Physics, time, and life are woven together in the tides. When you stand at the shore and watch the water rise, you are watching all three at once. You are watching gravity made visible. You are watching deep time made tangible. You are watching the pulse of life, the rhythm that has shaped evolution for billions of years. And you are part of it. You are not an observer standing outside the system. You are in the system. Your body is mostly water. That water is influenced by the moon's gravity, however slightly. Your ancestors evolved in tidal pools, learned to breathe air in the intertidal zone, walked onto land because the tides trained them. You are a tidal creature. You are a product of the moon's influence. And when you watch the tide come in, you are watching your own history. Close your eyes again. Imagine you are that water molecule once more, tumbling in the ocean. But now you understand the full story. You know that you are being pulled by the moon 240,000 miles away. You know that the moon is slowly moving farther and that billions of years ago it was much closer. You know that the rhythm of your movement, rising and falling twice a day, is the same rhythm that shaped the evolution of life on Earth. You know that the tides are not just water moving, they are time moving. They are life moving. And you are part of it. You are connected to the moon, to the sun, to the earth, to every living thing that has ever adapted to the tides. You are connected to the fish that first walked onto land, to the barnacles clinging to rocks, to the ancient corals that recorded the length of days millions of years ago. You are connected to the cosmos, not metaphorically, literally. The same force that holds galaxies together is moving you right now. The same rhythm that has played for 4.5 billion years is playing through you. You are not separate. You are part of the whole. There is a kind of gratitude that comes from understanding, not just knowing facts, but really seeing how things fit together. When you understand the tides, you see the moon differently. It's not just a light in the sky. It's a partner, a companion, a force that has shaped the earth and everything on it. When you understand the tides, you see the ocean differently. It's not just water. It's a living, breathing system responding to invisible forces, carrying the memory of deep time. When you understand the tides, you see yourself differently. You are not a separate being, isolated and alone. You are part of a vast interconnected web of matter and energy and time, and there is something deeply comforting about that. You are part of something larger, something ancient, something beautiful. The tide is coming in. It has been coming in and going out for 4.5 billion years. It will continue for billions more until the sun expands and the oceans boil away, or until the earth and moon become locked in a final silent embrace. But for now, the rhythm continues. The moon rises, the water rises, the moon sets, the water falls. Twice a day, every day. A rhythm older than mountains, older than continents, older than life itself, and you are standing in the middle of it, watching it unfold. The water is rising around your feet, not because of wind, not because of storms, but because the moon is pulling it. Across 240,000 miles of emptiness, the moon is reaching down and lifting the ocean. And you, standing on the shore, breathing the air, alive in this moment, you are a witness. You are part of the story. You are a note in the symphony, a wave in the ocean, a moment in deep time. Let's return to where we began. You are standing at the edge of the ocean at midnight. The moon hangs above you, silver and silent. The water is rising. But now you understand. You understand that the moon is not just pulling water. It's pulling space-time itself, creating a curvature that the ocean has no choice but to follow. You understand that there are two bulges, one toward the moon and one away, and that you are rotating through them. You understand that the earth is slowing down, that the moon is moving away, that the day is getting longer, that time itself is stretching. You understand that the sun is also pulling, that its tides interfere with the moon's, creating the monthly rhythm of spring and neap. You understand that the tides shaped the evolution of life, that your ancestors learned to breathe air in tidal pools, that the rhythm of the ocean is written into the biology of countless species. You understand that you are not separate from any of this. You are part of it. The moon's gravity is pulling on you, right now. The Earth's rotation is carrying you through space at 1,000 miles per hour. The water in your body is responding to the same forces that move the ocean. You are a tidal creature standing on a tidal planet orbiting a star in a galaxy that is itself moving through the universe. And the tides, the rising and falling of the ocean, are the visible manifestation of all of this. They are gravity made visible. They are time made tangible. They are the pulse of life. They are the heartbeat of deep time. And they are here, right now, at your feet. The tide comes in. The tide goes out. The moon rises. The moon sets. The universe breathes. And you are part of it.